Intuitively, what is this measuring intuitively? What's the intuitive formula for this that you use to interpret its meaning? Right. Right. Now, Jacob, from what we said earlier, what should you be able to show this is equal to? Exactly right, -1. And let's just verify that. What is partial x, partial px? It is going to be what? What's partial x, partial px? Anybody? Okay, -1/2 I. Exactly. That's partial x, partial px. Multiply this times px over x. But what is x? X is 1/2 I px to the -1. But multiply these two terms here. You add the exponents. This numerator becomes -1/2 I px to the -1. In the denominator, you have 1/2 I px to the -1. So obviously, this ratio is -1. This is -1. So that verifies. Whenever you have a multiplicative form like this, the exponents give you the elasticities. Okay. So the fact that my price elasticity demand for good x is -1, my own price elasticity demand for good x is -1, means what? In simple words. It's unit elastic. And what does that mean?
1% change in price, increase in
Okay.
price will decrease consumption of good x by 1%.
Right. Equal percentage changes, but in the opposite direction. You're right. If price goes up, by the law of demand, then consumption has to drop. So price goes up 1%, quantity demanded drops by 1%. If price goes up 2%, quantity demanded drops 2%. If price drops by 3%, quantity demanded would go up by 3%. Okay, that's what it means. Okay, and finally, what is the elasticity of good x with respect to the price of good y? Now, we would call this a cross-price elasticity. We would call that a cross-price elasticity. And mathematically, this would just be partial x, partial py times py over x. Now, can anybody tell me what this cross-price elasticity will be? 0. Because we already know the partial x, partial py is 0. So this cross-price elasticity is 0. Okay. So is this one. There's another cross-price elasticity. We could say, what is the elasticity of good y with respect to the price of good x? This would be partial y, partial px times px over y. That would also be 0. By the way, you know, we started off by calling them x star and y star, emphasizing their optimal values of x and y, but a lot of times people will just drop the stars because that's understood, that they're the optimal values. Okay, so a lot of times the book won't even put the stars because it's already understood that you're assuming utility maximization in order to derive these Marshallian demand curves. Okay, so sometimes they'll just write it as x equals I divided by 2px. Sure, sure.
So
Shoot.
we're saying that the price of y should have no effect on
In-
the amount of tax we
Right. For me, given my utility function. Given this utility, u equals x times y. Yes.
If we had assumed that y cost $201 and our budget was $200, we obviously have to increase our consumption in x in order to maximize utility, right?
No. What all that would mean, these formulas are quite general. So you still would find the optimal values of x and y, and then they might be fractions. For example, the consumption of good y, if the price of good y was 201, you still would plug in here, and you would get a value. But it might be a fractional value of y. So y might be less than 1, but that would be okay. Yeah, right. So these, there's really no restrictions. The only restriction is we're assuming the price of x is positive, the price of y is positive, and income is positive. Okay. You would have a problem if you let the price of x be 0. That would be a problem because then you can't divide by 0 here. So we're assuming that the price of x is positive and the price of y is positive. But you could, plug into those formulas and out pops the optimal values for x and y, regardless of what the price of x and the price of y are. So there's really no restrictions. Let me just show you what's happening on an intuitive level. Right, in this example we did here, we were assuming that I was 200. We were assuming that the price of y is 1. The price of x is equal to 4. Okay. Now, suppose income were to increase. What would happen in our diagram if, say, income were to increase? How would our diagram change?
Well, the budget line would shift.
Yeah.
Our income increased, the budget line would shift to the right.
Right. The budget line would just shift to the right in a parallel fashion. And it's obvious if it shifts to the right in a parallel fashion, what you're going to do, it's supposed to be parallel, is you would increase your consumption of both x and y. Now, if the price of good x were to fall, in this example, suppose we hold income constant at 200. The price of y is 1, but say the price of good x is 2. Then what would happen in this diagram right here? Yeah, the slope changes, and what would happen to the slope of the budget line if the price of x were actually to decrease?
It would shift outward, keep holding constant the y-intercept.
Right. So, but it would become flatter. Yes. So now you draw this. Here's the original one. Let me redraw the original one. Here's x. Here's y. Here's 200. Here's the 50. But now that goes for this price of x and the price of y. But now if the price of x were 2, it would look like this. Okay, so it would become flatter like that. Okay. And obviously, consumption of x would increase. But what about the consumption of y? In this case, if you work this out, I'll just tell you what the solution will be. In this particular case, you're always at the midpoint. So you'd be right here and right here. So your original indifference curve is tangent right here. Your new one's going to be tangent right there. So it works out that the value of y will stay exactly the same, but the amount of x goes from 25 to 50. Okay. The law of demand. As the price of x falls, you consume more of good x. Okay. All right.
Are there examples where the optimizing formula is not at a midpoint on the budget line?
Yes. Yes, we need to. We will I'll make sure I illustrate that. I think on your homework problem, it worked out to be, I believe, on the midpoint too, didn't it? I can't remember. It didn't? Okay, so that would be an example. Okay. I think, what it was is, in this case, utility is x times y. X and y both have the same exponent. That's why you're getting that midpoint as this optimal solution. But if those two exponents on x and y are not the same, then you get a different result. Okay. Just a few more general points I'd like to make before I let you go. Oh, actually, there was one thing I neglected to do. Did I neglect to show you the second order conditions when I drive the Marshallian demand functions? I think I neglected to show you those for the general case. Let's do that. We had this. We wanted to maximize this subject to I equals pxx plus pyy. Okay. So let's just quickly run through this again. In this case, our Lagrange function was this. Okay. Recall that z sub x was this. Z sub y was this. We don't even need z sub lambda for the second order conditions. Our constraint function g is just this, pxx plus pyy. All right. So let's look at our bordered Hessian for this problem. Our bordered Hessian is this: 0, gx, gy, gx, gy, zxx. Oh boy, this is zxy. Let me switch. That's not showing very well. No, this is, doesn't look any better. zyx, zyy. Okay. Now, in this case, what is g sub x? Ian, I know you're anxious to get out in the sunshine. There's still a little bit left. So what is g sub x?
G sub x would be negative.
Oh. Okay.
Oh, yeah, just out of yes.
Yes, p sub x. Now, what we are assuming about the price of good x, we are assuming that's positive. What is a g sub y? Partial derivative of g with respect to y. Right. Okay, so now we have our borders. Okay. All right, what is z sub xx? I don't think I did this, did I? I hope I'm not repeating myself. What is z sub xx?
0.
Right. Okay.
Done so far.
Okay. Z, okay, what is ZXY? Zach? 1. Okay. This is 1, that's 0. We did it for specific values of P and X and PY, but we didn't do it for the general case. So, what's our bordered Hessian now? It's a little more complicated. It's 0, it's minus px times the determinant. And this determinant is, it's minor, is px 1, py 0. Plus py, we're going across this top row, times the minor of py, which is px 0, py 1. So what is this going to be? This is going to be 0 minus py. So, okay, doesn't look good. This does not look good. What? Oh, okay, I got you. It's 0. Yes, it's minus py times the minus px, so that's px py. Good. Thank you. I know this had to be positive. Because, see, this determinant here is minus py, but that's multiplied by minus px. So it's plus px py. What do we have here? Py times px. So we get another px py. So this is 2 px py. So that is positive. So those optimal values of x and y we solved for earlier, those were the optimal values. Because the bordered Hessian is always positive. Okay, so that guarantees a maximum. Yes, yes. The only thing you have to do is you have to be careful. If you pick the top row, yeah, you start with a positive, negative, positive. But if you start with a different row or a different column, then it changes. So, but you just have to be careful of that. Okay. Actually, you can determine the sign of the minor by looking at whether the subscripts of the element are odd or even. This is the element 1, 1. 1 plus 1 is an even number. So this is a positive. This is the element 1, 2. 1 plus 2 is odd. So that's why you had to multiply this by minus. This is the element 1, 3. 1 plus 3 is 4. Even number. So you multiply that by plus 1. If you were to start with some other row, you would have to remember that to get the signs right. Okay. Okay, so we know that those values for x star and y star that satisfy the first order conditions give you maximum utility. Okay. You know what this corresponds to? The fact that this bordered Hessian is positive, it can be shown that that's equivalent to the indifference curves being convex. As long as the indifference curves are convex in shape, then the tangency will always give you a maximum. Okay. Or just a few more items quickly, and then I'll let you go. In all the examples we've done so far, it was assumed that you had a functional form for the utility function. Now let's make our results even more, a little more general. Let's just assume the following, that you want to maximize this. U, which is a function of x and y. But we're not going to say what that function is. subject to this. I equals pxx plus pyy. In this most general problem with two variables, the Lagrange function would just be this. Z equals u of xy plus lambda times I minus pxx minus pyy. The first order conditions would just be this. Z sub x equals u sub x minus lambda px equals 0. Z sub y would just be u sub y minus lambda py equals 0. And of course you would have z sub lambda equals I minus pxx minus pyy equals 0. That's just the budget constraint. Now notice, if you just solve for lambda from these two conditions, what do you get? You get lambda equals, from this equation, u sub x divided by p sub x. Lambda from this equation gives you u sub y over p sub y. So this is the first order condition. And this has a nice intuitive interpretation. What is, look at this, u sub x, forget about the lambda part now. We require that u sub x over the price of x equals u sub y over the price of y. In other words, we require that the marginal utility of good x divided by the price of good x be the same as the marginal utility of good y over the price of good y. Okay. So in order to maximize utility, you must be consuming at a point where the marginal utility of each good divided by its price is the same across all goods. This result generalizes to the case where you're consuming n goods. You have the same result. The marginal utility of each good, say the marginal utility of good 1 divided by the price of good 1, has to be the same as the marginal utility of good 2 divided by the price of good 2, equals dot, 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 the marginal utility of good n divided by the price of good n. Okay. In the optimal solution, the marginal utility of each good divided by its price has to be the same over all goods. Okay. Now, so that has a very intuitive interpretation. Furthermore, let's write this out, and let me show you that lambda star is just this constant ratio. Okay. Look at, interpret the marginal utility of good x. Let's write the marginal utility of good x this way. It is just delta u over delta x.